Hi everyone and welcome back to our machine learning course. I'm Anna Vetteruzzo and today's lecture is all about fine-tuning techniques for transformer models. Today we are going to talk about the transformer model, just a quick recap from the previous lecture. I will then introduce the main differences between pre-training and post-training techniques, but we will mostly focus on supervised fine-tuning techniques and in particular parameter efficient fine-tuning. We will then delve into LoRa, which is one parameter efficient fine-tuning techniques that is largely used in the literature, and some advanced insights into LoRa. But let's get started. The architecture follows a classic encoder-decoder structure where the encoder extracts information from the input sentence and it provides this information to the decoder to make the final prediction. The input sentence is first converted into embeddings or token, and then a positional encoding is added to each token to capture information about the order of the words in the input sentence. The token then passes into the encoder and decoder layers. Both the encoder and the decoder consist of multiple transformer blocks with the self-attention layers that is used to learn interaction between the tokens, normalization layer to normalize the inputs, residual connection to preserve the gradients, and finally feed-forward layers to learn the mappings. Finally, the output passes through a linear layer and a softmax to produce a probability distribution over the vocabulary and generate the final predictions. We also know now that there are different variations of this architecture. Indeed, we have the standard encoder-decoder models architecture, such as the T5 model, which was very popular in 2018. And these architectures are ideal for sequence-to-sequence tasks, such as translation. But most recently, people are mostly focusing on decoder-only architecture, such as the GPT series or also the Gemini series, where the idea is that we can generate text using the next token prediction objective. This architecture rely on a masked causal self-attention, where a token at position I only attends to the tokens at the previous position. And finally, we also have what is called the encoder-only architecture, such as the BERT model that extracts sentence embeddings. And the main idea is that in this architecture, a token at a position I can attend to all tokens in the previous and also in the next position. But in this lecture, the main focus would be on decoder-only models, which are very popular nowadays and are also at the basis of large language models. So large language models are called LLMs for short, and these are large decoder-only models that usually consist of hundreds of billions of parameters. And it's important to notice that people are always scaling up these models as much as possible because they realize that the larger the model is, so more parameters the model has, and the better is the performance. For instance, you can see in this plot that is taken from this very famous paper called Scaling Laws for Neural Language Models, that if we increase the compute needed for training our model or the dataset size, or again, the number of parameters, then we have a huge decrease in the test loss. But on the other side, this will also end up in an increase in the cost because training very large language model requires a lot of compute, which goes together with a lot of money. So you can clearly see here that training a model from scratch for a single task is not feasible. The solution is to divide the training pipeline into different phases. And in particular, this is the pre-training and the post-training phase. And we will quickly see what these phases usually do to the model. So in the pre-training phase, our large language model is trained with massive amounts of raw data sets, such as Wikipedia pages, web pages, or books. And the idea is that we want to have what is called a base model, which is a model that has a very broad and general knowledge, but it is only able to predict the next token. So it's not able to follow an instruction or to reply to us in a chatbot way. So this is not exactly what people would like to use in their daily life. And that's why most of the time we need a post-training phase. And in this phase, the main goal is that we want to refine the pre-trained model to behave in a specific, useful, and safe way. And there are different methods that can do this. One of these is the supervised fine-tuning, where the idea is that we adapt the model to a specific task or domains via some high-quality data. And the outcome is what is usually called an instruction tune model. And then another kind of methodology is the preference tuning, where we want to ensure that the model responses are in the correct format, they are helpful and also harmless. And usually this is done through reinforcement learning methods such as direct preference optimization and reinforcement learning with the human feedback. Most of the time, these two SFT and preference tuning methods are actually combined in the post-training phase. So you always need to think about these two methods and not as two different alternatives, but mostly as two different methods that can be used together. The focus of this lecture will be on supervised fine-tuning, and in particular, as I said before, in parameter efficient fine-tuning. So you can see here, if you think about this new training pipeline where we have this pre-training phase first and this post-training phase afterwards, you can see that there is a paradigm shift from traditional machine learning and deep learning way of training models. Indeed, in traditional machine learning or deep learning, we usually train a model for a specific task. Or alternatively, if we have a pre-trained model, we can always try to transfer its knowledge of this pre-trained model to solve a different task through transfer learning, for instance. But what LLM training is doing is something slightly different, because here the idea is that we want to train a very general model that has a lot of different information from all different fields. And then we want to post-train or fine-tune this model for a specific end task. So let me show you an example with a simple prompt, how a base model and an instruction tune model can reply to you. Let me just remind you that a base model went only through the pre-training phase, so is only able to do next token prediction. While on the other hand, an instruction tune model is a pre-trained model that has been adapted with SFT, for instance, and also other techniques in order to follow instruction. Let's assume that we have this very simple prompt. What is the capital of the Netherlands? And then we take a large language model such as Llama 3.2. In particular, for this exercise, we took a quite small one because it's just 1 billion parameters, just for simplicity and for the sake of inference. And this model, as you can see, is simply pre-trained. And it's answering our question with another question, right? Because it's telling us what is the time zone in the Netherlands, what is the population of the Netherlands, and so on and so forth. So you can see here that the model is not able to properly answer to our question, but it just like generates some more prediction that could complete the prompt that we have. But this is actually not what we want to have. Because like a user that asks a question to a large language model would like to have an answer from this question, right? And this is exactly what the instruction tune model is doing. Because if we take exactly the same pre-trained model, but then we apply SFT on top, we obtain this instruction tune model that you can see on the bottom part. And you can clearly see here that is able to answer the prompts with the correct answer, saying this is Amsterdam, the Netherlands is a country located in the Western Europe. It is known for its rich history, beautiful canals, and vibrant culture. So he first generates an answer to the question, and then he continues by providing more and more information to it, which is exactly what we are expecting from the human perspective. So let's have a look at how we generated these responses. So I pasted here some Python code that you could also run on your laptop or in Google Colab if you want to use a GPU and make everything a bit faster. And the idea is that first we need to authenticate to Hugging Face because the model that we used are downloaded from Hugging Face. So you can simply pass here your Hugging Face token, and then you just directly log into it. You define the base model name, which is the name of the base model that you would like to use for the generation. And then you need to do the loading phase. So you need to load both the base model and also the base tokenizer, because always remember that a large language model is only associated with a specific tokenizer that was used during the training phase. And then once you do that, you can simply define a prompt. You need to tokenize the prompt with the tokenizer that you have loaded before. And then once you have done that, you can just call this generate function, which is an Hugging Face-based function, by providing this tokenized token in input and setting the maximum number of tokens that you want to generate. In this case, it was set to 150, but you can play a bit with the codes and set different numbers and see different type of generation. And then once you have your outputs, always remember that these outputs is not like text, but consist of different tokens. So you always need to call the tokenizer again to decode these tokens, and then you can print the sentence, the output sentence. I would like also to remind you that the generation of a large language model is always randomic. This means that if you run this code multiple times, you might obtain completely different answers. So always take this into consideration when you run your code. And then I also pasted here exactly the same code, but with the instruction tune model. So as you can see, the script is exactly the same as before, but what we need to change now is the model name, because now we are using this Llama 3.21b instruct model, because this model went through the all pre-training phase like the base model before, plus a supervised fine-tuning phase that allow it to be fine-tuned with different instruction, or in other words, instruction tunes. Cool. So let's go a bit more into detail into this supervised fine-tuning phase now. So SFT is also called instruction tuning, and the main idea, as we already saw, is that we want to adapt the pre-trained model using some labeled input-output pairs to improve the performance and the instruction following capabilities of the pre-trained model. And how can we do that? So first of all, we need to collect some pairs of input-output with the desired behavior. This means that these pairs needs to mimic the behavior that we want our model to have after this SFT phase. And then we can use the same objective function that we were using during the pre-training phase, which is the next token prediction, as you probably remember. But the main difference now is that during the instruction tuning phase, we provided the all input tokens to the instruction tuning model, and then we compute the loss value only on the output tokens. So if you look at this image in the bottom of the slides, you can see that during the pre-training phase, we compute the loss value on each output token, because what we are interested on is in this the next token prediction objective. But on the other hand, during the instruction tuning phase, we want to provide in input the all questions and just compute the loss values on the tokens that correspond to our answer. It's also important to notice that the standard SFT approach is also called full fine-tuning, or a full FT for short. And in this approach, all the model weights of the large language model are updated during the process. How do the data look like, the one for instruction tuning? First of all, these are very high quality data. And as I already said before, they should explicitly mimic your task that you want and the behavior that your model should have after the fine-tuning phase. They can be both human written or synthetic data, and they are usually much less than what we have during the pre-training phase. Because during the pre-training phase, we usually talk about trillion of tokens, but during the post-training phase, instead, we just have millions or a few billions of tokens. Depends on the model size. So as you can see here, we can have data from different tasks, and such as summarization, question and answering, classification, or creative writing. And this depends a lot on how you want to fine-tune your model. So if you want a model that is very good at answering your question, you will have to prepare or collect some post-training data that looks exactly how you would like your model to answer you. For instance, you might have an instruction that says, why do people like comedy movies? And then the response of the model should be something like, comedy movies offer stress relief, social bonding, and an escape from reality. And you can abstract this to any task that you would like to do, like math problem, or helping with some Python codes or creation of JSON file, whatever. The most important part is that your data, again, should clearly reflect the model behavior that you want to obtain at the end of the instruction tuning phase. Of course, there are some challenges of full fine-tuning. As I said, it requires very high quality data. There is a risk of overfitting on small data sets. It needs to store the full model checkpoint for each fine-tune model. And this is a big problem if you consider that the large language models nowadays have so many parameters and require so much memory to be stored that is actually difficult to find some cloud system service that they can keep all of these parameters in the memory. And then there is the risk of catastrophic forgetting, of course, because during the SFT phase, what we are doing is that we update the original knowledge, so the original weights of the pre-trained model. So there is always the risk of forgetting what the model has learned before. And finally, it is very computationally expensive, right? Exactly because you are updating each weight inside this huge model. So how can we solve this? The answer is we can apply different techniques. So instead of updating each single weight in this huge model, we can instead use some techniques called parameter efficient fine-tuning, where we update only a small set of parameters while the others remain frozen. And you can see in this slide some pros and cons of both the techniques, because in full fine-tuning, for instance, you have very high flexibility because you are updating all the weights, right? But on the other hand, it is very computationally intensive. It requires large memory. There is low adaptability to diverse tasks because even if you have 100 tasks and you need to run this SFT phase for all the 100 tasks, is very, very expensive. And also it takes longer to train this model and to fine tune this model. On the other hand, if you apply techniques such as parameter efficient fine tuning, for sure you will have a low forgetting, right? Because now you're not touching all the original weights of the model. And sometimes you don't even touch these weights at all, but you simply use some additional parameters that you embed into the base model weights. Second, of course, it is less compute and also memory intensive. It has a very high adaptability to various tasks, but the main issue is that it might require choosing different type of parameters per task. Cool. So let's try to look at an example. Let's say that I want to fine-tune a 7 billion parameter model using full fine-tuning. If I want to do that, this would require 50 gigabytes of VRAM. While if I want to fine-tune the same model using a parameter-efficient fine-tuning technique, such as LoRa that we will see a bit later in this lecture, you actually need only 20 gigabytes, which is less than half of what you needed for full fine-tuning. And of course, the actual memory usage depends on many factors, many hyperparameters, but this is just to provide a rough idea of the gain that you can get by fine-tuning models using parameter-efficient techniques. Let's talk now about the different parameter-efficient fine-tuning methods that there are out there. The most famous one are prompt tuning, adapter layers, and LoRa. In particular, in prompt tuning, the main idea is that we want to learn some soft prompts through backpropagation that will condition the pre-trained language model to perform some specific tasks. Or in other words, the idea is that we want to append some tunable tokens to the input tokens that can be fine-tuned during the fine-tuning phase such that they carry information about the task that we are using for fine-tuning purposes. In adapter layers techniques, instead, the idea is that we have our decoder-based transformer architectures, right? And we want to add some adapter layers within this architecture such that during the fine-tuning phase, we only need to tune the weights inside the adapters. And most of the time, the adapters consist only of one or two non-linear layers. So these are very simple MLPs that at the end will provide information about the language model, about the task that we want to solve. And finally, probably the most used technique nowadays is LoRa, which stands for low rank adaptation. And the idea here is that we can approximate the weight updates of the large language model with some small tunable matrices. So please look at the difference between adapter layers and LoRa here, because for adapter layers, the idea is that we want to add more parameters within the transformer encoder layers that we can fine-tune for specific tasks. But for LoRa, the idea is different. For LoRa, the idea is that we can approximate the weight updates, so the updates of these huge weight matrices inside our transformer architecture with some small matrices that we can fine-tune. Cool. So let's go a bit more into detail about the LoRa approach. In this second part of the lecture, we will mostly focus on this specific approach because it's one of the most used in practice nowadays. So let's look once again at the architecture of the decoder transformer. So you know already that there are different weight matrices that we need to learn in order to pre-train or fine-tune our model. And these matrices are huge. For instance, in the case of GPT-3 with 175 billion, each weight matrix has a size of 12,000 by 12,000, more or less. And you can clearly deduce here that if you want to fine tune each weight in each single matrices, then this becomes very computationally expensive. But what LoRa is doing on the other end is that instead of learning the update for each weight that we will call delta W, we can approximate it using a technique called low-rank approximation. This means that delta W is equal or can be approximated with two matrices that are called A and B in these cases, multiplied by lambda, which is just a scaling factor, which is usually set to 1 or 2. And these A and B matrices are considerably smaller than the delta W, which is the weight matrix of the original pre-trained model. And in particular, the size of A and B depends from this rank, which is here called the R in short. And we will see in a few slides what is the impact of this hyperparameter and how to set it correctly. So how can you do gradient descent with LoRa? Let me first recap a bit what the stochastic gradient descent is. So the first step that we need to do in order to run a mini batch stochastic gradient descent is to draw a batch of training data. And then we pass these inputs batch of training data into the network, and we generate some prediction that we will call y-ads. Then we compute the loss that in case of large language model is simply a cross entropy loss between y-ads and which are the predicted labels and y that are the true labels. And then we need to do the backward pass. And in particular, to do the backward pass, we want to compute the gradient of the loss with respect to each single weight. We backpropagate the gradients through all the layers. And finally, we can update the weight matrix in this way here that you can see in the slide. And you just need to repeat this for an epochs through the entire training set. Cool. When we use LoRa instead, we are not computing the gradient of the loss with regard to each single weight of our model, but we just focus on the LoRa weights, where the LoRa weights, as I said before, are just some very small with respect to the original matrices, very small matrices, A and B, that will approximate the update of the original matrix. So as you can see here, you compute the update of the matrix A and the matrix B. And then the fine-tune weight matrix can be simply expressed as Wi plus 1 is equal to Wi, so the weight matrix at the previous step, plus the multiplication of lambda, B, and A. Cool. What are the benefits of LoRa? Well, for sure, we have a reduction in memory and storage. And this is because, of course, we update only these very small matrices. And these are the only matrices that we actually need to store in the memory. We also have a reduction of VRAM GPU consumption. It is very easy also to switch between tasks because you can consider that you have a single pre-trained model, right? That is maybe stored somewhere on the cloud or in some platform like Hugging Face that you can easily download. And we have already seen how to do that. And then locally, maybe in your laptop or in some cloud, you have your LoRa matrices for different tasks. And what you can do, you can simply plug and play these LoRa matrices on the pre-trained model and be able in this way to solve different tasks while storing only these small LoRa matrices. Then we also have a 25% faster training compared to full fine-tuning. And there is no risk of catastrophic forgetting, of course, because we are not updating any weights of the original pre-trained model, but we are just updating the LoRa weights. So this table is actually taken from the original LoRa paper that you can just check out going in the link here. And it showed the comparison between a GPT-3 full fine-tuning, where you can see that the number of trainable parameter is 175 billion, which is the total size of the model. And then there is a comparison with some prompt tuning methods, some adapter-based methods, and the LoRa, of course. And the two different rows for LoRa here reflect two different variations where some LoRa hyperparameters were, for instance, the rank, were set in a different way. And you can see that there is a considerable reduction in the number of trainable parameters with LoRa compared to full fine-tuning. But on the other hand, the accuracy remains like exactly on pairs, if not like a slightly better than the full fine-tuning techniques. So let's now move towards a few exercises. First of all, I would like to show you how much memory we can save by using LoRa instead of like full fine-tuning. And now, let's do it as an exercise through some quantitative measure. So let's assume that our LLM has complete weight matrices with 10,000 rows and 10,000 columns, which means a total of 100 million parameters. And then let's assume that we want to use a LoRa with a rank equal to 8, which means that our A matrix has 10,000 rows and 8 columns, while B has 8 rows and 10,000 columns. This will result in a total of 160K parameters, which is 600 per less than the 100 million parameters that we had in the original weight matrix of the LLM. Another exercise instead is how we can calculate the number of trainable parameters in LoRa. So you can see here that the number of trainable parameters can be computed by multiplying 2 by this L LoRa factor, which is the number of weight matrices that we apply LoRa to, the size of the model, the hidden layer size, and the rank. And you might wonder why we need these two in front of the equation. And this is because always remember that each LoRa consists of two matrices, A and B. Cool. For L LoRa instead, which is the number of weight matrices we want to apply LoRa to, I will discuss a bit more about this in the next few slides. But just to give you an idea, what does it mean? The idea is that LoRa can be applied to any metrics in the original LLM. For instance, all the matrices in the self-attention layers and also the feed-forward layer. But for instance, in the original paper, LoRa was only applied to the query and value matrices in the self-attention layer. So this is a design choice and an hyperparameters kind of that can be tuned. But we will see some recommendation about how to set these parameters in the next slides. But before looking into this, let's have a look at how we can use LoRa with some Python code. So let's first consider and load a dataset that is available online. In particular, these datasets, if I'm not mistaken, is available in Hugging Face. So you can use the load dataset function from Hugging Face. Then we need to tokenize our samples. And just for simplicity, we are here just taking 50 samples instead of the whole dataset, which is very big. And if we display it, we will see that there are 50 rows, so 50 samples in total. And each sample has these features that you can see here. What is important to notice here is the prompt features, that is actually the part that we tokenize. The input IDs that provide information about the position of the tokens in the sample sentence, and the attention mask. Cool. So then we need to define a model name. For this specific exercise, we use the Bloom with the 500 million parameters, just because it's pretty small and very fast to train. We load the model, we load the tokenizer, but we have already seen how to do this. And then what is very important is that we need to define some LoRa config. In particular, we need to define the rank to set the number of trainable parameters, so the size of the A and B matrices that we saw before. We need to set the alpha parameter, which is a scaling factor that simply adjusts the magnitude of the weight matrix. And if you remember before, there was this lambda parameters in our slides, which is actually just the fraction between A and R. So usually, actually, A is set equal to the rank, even if it's not the case in this example. Then we need to define some target modules, which are the name of the modules that we want to apply LoRa to. Because as I mentioned before, LoRa can be applied to feed-forward layers, to query matrices, to key matrices, value matrices, and so on and so forth. And I really recommend you to check the name from of these modules based on which model you are going to use. Then we have some dropouts for avoiding overfitting. We need to decide whether we want to train also the bias parameter or not, and some simple task type. What is very important after setting this LoRa config parameter is that we create a PEFT model. This can be very easily done by using the getPEFT model method that is already available. And just by passing the name, the loaded model, and the config of the LoRa. And this method will automatically create some LoRa matrices that will go together with the model that we loaded. And then we need to define some training arguments. And also here there are different hyperparameters that you can set, such as the output directory, the learning rates, the epochs, and if we want to report the results to WandaBee with biases or not. And finally, we define a trainer. So the trainer takes in input the PEFT model that we created, the training arguments, and the training dataset that we want to use. And we then just need to call the train function from this trainer. And once we have done that, this should be pretty fast. If you use a GPU in particular, we can save our model, and then we can load it whenever we need it. And what is very important to notice here is that the save and load function that are used in this Python script actually will just save and load the LoRa weights they will not save the pre-trained weights of the model because that will not be efficient and effective, since these weights are already available online. So why do we need to use our own local memory in order to save them while we can just download them from the web? So this is very important to take into consideration, and this is also one of the cases why a lot of people are using LoRa nowadays, because in case of budget constraint, they can still train and fine-tune their models. And finally, once we have done this fine-tuning phase, we can, of course, do some model inference and generate some output to verify whether everything went well and if our model is indeed fine-tuned with the task that we wanted. And to do that, we can simply use this generate function that we have also seen before. Again, there are some parameters to set. Feel free to look into them. We then need, again, to have an input prompt, input sentence that we will tokenize. And then we need, remember to also decode with the tokenizer what we have generated with the get output function. And you can see here an example. In particular, my input prompt was, I want you to act as a football coach. And the output of the model is, I will provide information on current events and offer suggestions for actionable tactics that can help improve performance in order of improving team performance, and so on and so forth. So we have now seen the full pipeline of how to load a data set, to load a model and the tokenizer, to define some training hyperparameters, to create a LoRa module and to attach or combine this module with the model that we loaded, how to train LoRa, which in other words is how to fine-tune our model, how to do inference, so generating the output, and also how to save and load the model. Cool. Let's talk now about some interesting insights into LoRa. In particular, we want to look at the role of the rank and the scaling factor that we have already mentioned multiple times in this lecture, but we've never really understood what this represents. In particular, the rank, as we said, already controls the number of trainable parameters, because if you remember from some previous slides, the A and B matrices within our LoRa, actually, their size is controlled by these rank parameters. And when you have a small rank, you have fewer parameters and less memory consumed, and the fine-tuning phase will be faster. But on the other hand, you always need to compromise, because if you have a complex task, a small rank might lead to very bad performance. So common values of this rank are usually between 4 and 256. And this is based on both the task complexity and also the size of the pre-trained model. And then we have lambda, which controls the magnitude of the weight updates. And as we already mentioned very quickly, lambda is usually defined as alpha over the rank. And usually it is set to 1 or to 2, because tuning it is the same as tuning the learning rate of the optimizer. So recently people just prefer to tune the learning rates and leave alpha equal to 1. Another question that you might have is, what is the best way and where do we want to apply LoRa? So as I said before, LoRa can be applied to different matrices in the transformer decoder. And in the original paper, LoRa was only applied to the query and the value matrices within the self-attention layer. But more recently, people have found that applying LoRa to all self-attention matrices, so also the key metrics and also the feed-forward layers, really help. But you can find more recommendation on how to set these LoRa's hyperparameters in this Onslaught hyperparameter guide that I really recommend you to check. Cool. So now that it's clear to us what LoRa is and what full fine-tuning is, what is the difference in terms of performance and sample efficiency? And unfortunately, there is no agreement between the research community. And in the next few slides, we will see three different work that have completely different visions. For instance, this first work, that is actually a very detailed blog post that I recommend you to read, is called LoRa Without Regrets. And they claim in this blog post that LoRa can be on par with the full fine-tuning in terms of performance, but only if some parameters of the LoRa modules are set correctly. And these parameters are four. The first one, they say that the dataset that we are using for fine-tuning doesn't need to exceed the LoRa's capacity, meaning that this needs to be a small to medium-sized dataset. The second factor is that we need to use a sufficiently high rank to capture all the task complexity. Indeed, you can see from this plot that while they were fine-tuning this llama model with 8 billion parameters on this specific Tulu3 dataset, is a very common dataset used in fine-tuning research, you can see that the higher the rank and the closer the test loss is to the full fine-tuning technique. The third factor is that the optimal learning rate for LoRa is usually higher by a factor of 10 than for full fine-tuning. And once again, this is represented in these plots that is taken from this blog post. And this makes a lot of sense, right? Because in full fine-tuning, you have a lot of weights that you need to optimize. And you do the fine-tuning stage for very long time. So the learning rates need to modify the weights in a very small way because you have a lot of time to do that. But on the other hand, when you use the parameter efficient fine-tuning, such as LoRa, you want to be faster. You have less weight to optimize. So you want to get closer to the optimal to convergence, so the optimal values for the weights as fast as possible. And finally, the last parameter is that LoRa needs to be applied broadly, meaning that it needs to be applied to the self-attention metric and also the feed-forward networks. Then there is another work from 2024 that instead is claiming something different. They are claiming that LoRa cannot match a full fine-tuning. And they claim that this is just an illusion. So people that says that LoRa match full fine-tuning only live in an illusion. And this illusion is usually due to insufficient optimization or testing on limited data sets. Indeed, they says that LoRa can match full fine-tuning in terms of performance only if the task is very, very simple, such as classification or very simple instruction tuning techniques. But when the task becomes a bit more complex, such as with the code or long-form text generation, then LoRa struggles. And finally, we have the third paper, which is LoRa Learn Less and Forget Less. That's particularly highlight that full fine-tuning is usually more accurate in terms of performance and also more efficient than LoRa. But LoRa forget less of the original knowledge. So the takeaway from all these works is that it is unclear whether LoRa can match full fine-tuning, but for sure it is the recommended solution in case we are in budget constraint scenarios. And finally, I would like to conclude this lecture by quickly showing you some more advanced and the more recent optimization that have been done on the LoRa methods. And in particular, we have this quantized LoRa that is also called the QLoRa, in which the idea is that we want to quantize the weights of the LoRa matrices to make it even more efficient in terms of memory. Instead, we have with this QLoRa a 33% GPU memory savings, but we have an increase in runtime. Then there is DORA, which stands for weight decomposed LoRa. And in this case, the idea is that they want to reduce even further the number of weights that are updated during the fine-tuning phase. And this results in a 4% accuracy improvement. And finally, I also wanted to show you how LoRa can be integrated to extend the LLM capabilities to handle multiple modalities. In particular, there is this 5-4 multimodal paper that was released at the end of 2025, where the authors proposed to use a mixture of LoRas, meaning that different LoRas have been added to the original weights of the LLM to handle different modalities, such as images, text, but also audio. The idea is that based on the input token, a specific LoRa is selected based on the input modalities as well, and that would help the output generation of the multimodal model. So that was all for today. Thank you so much for listening to this lecture. I will leave you here some more information and useful material that you can check out if you want to delve deep into any of these topics. Thank you once again